It is a real privilege, a true honor, and a great pleasure to introduce the conference's first plenary keynote speaker, Professor Mircea Grigoriu of Cornell University. Professor Grigoriu received 2 undergraduate degrees in Romania. First, a civil engineering degree from the Bucharest Institute of Civil Engineering, and subsequently a degree in mathematics from the University of Bucharest. In 1973, he arrived in the US to work on his PhD at MIT with the late Professor Alan Cornell. After completing his doctoral dissertation in 1976, he served as associate professor at Simón Bolívar University in Caracas, research associate at McGill University, and visiting associate professor at the University of Waterloo before assuming a faculty position at Cornell University. Professor Grigoriu's research has focused primarily on applications of probability theory to engineering and applied science. He has made seminal contributions to various areas, including linear and nonlinear random vibrations, stochastic mechanics, stochastic calculus, system reliability, numerical methods for solving stochastic problems, probabilistic models for microstructures, wind and earthquake engineering, climate models, and Monte Carlo simulation. From all these groundbreaking contributions, my personal favorite is the development of the translation process concept and corresponding theory to model non-Gaussian processes. Translation process theory is mathematically rigorous and elegant, yet simple enough to be used in engineering and applied science, and has become the standard method to model non-Gaussian processes in mechanics. One of its major advantages is that it models numerous physical quantities in mechanics, like random dynamic input excitations and physical properties of uncertain structural systems in a natural, physically meaningful, accurate, and efficient manner. A true tour de force. Professor Grigoriu's pioneering research has been recognized numerous times, including the 1993 IASR Senior Research Prize, the 2002 EMI Alfred Freudenthal Medal, the 2005 ASCE Norman Medal, and the 2016 joint EMI SEI Nathan Newmark Medal, among many others. He is serving on the editorial board of numerous technical journals and is a past editor-in-chief of our own Journal of Engineering Mechanics. Beyond his over 200 influential papers in refereed journals, he is also a co-author of a book on random vibration and the author of 4 books on stochastic calculus, stochastic systems, linear dynamical systems, and non-Gaussian processes. It is a pleasure, an honor, and a privilege to introduce our first plenary keynote speaker, Professor Mircea Grigoriu.
Good morning from Ithaca. I'd like to thank to the organizing committee for the invitation to give this lecture. Many thanks to Professor Deodatis for his very kind words. I promise to do my best to stay focused during the lecture, which is a difficult task since I'm alone in my office talking to a computer. The lecture is about extremes of random functions. Following some examples, I'll discuss analytical and numerical methods for solving stochastic equation, and then review methods for estimating extremes. I focus primarily on extreme value theory and importance sampling. Then I focus on stochastic processes. What can go wrong with numerical methods used to estimate extremes? And what this numerical model must satisfy such that they are useful. I conclude with two applications, one on diffusion processes, it's a model for population growth, and the other one on fragility curves, which use essentially concepts of extreme value theory. Examples will be from dynamics, waves, and materials. Even simple dynamic systems, such as this linear half oscillator, can generate extremes. For this system, the input, it's an alpha stable process, which has stationary independent increments. The characteristic function has this form. So you may recognize that for alpha it's equal to 2, it represents a scale version of the Brownian motion. As alpha decreases from alpha equal to 2 here, 1.5 here to 1, two things happen in these two sets of sample of the state X. The size of the peaks increases, and the frequency tend to be less obvious, smaller. And also, there are significant differences when alpha is close to 1 between two different samples. These are records of wave heights above the still water level. The measurements are done with two different devices, which seems to be state of the art, yet they are quite different from each other. But I like to point out that there are peaks, relatively large peaks relative to the still water level, and these time series are clearly non-Gaussian. They are important because they become loads for offshore structure. Most metals consists or can be viewed as union of disjoint set called grain or crystals, within which the atomic lattice orientation is nearly constant. And the boundary between different grains is determined by these abrupt changes of the atomic lattice orientation. These drastic changes create stress concentrations and therefore extremes. The plot here shows a spatial variation of the effective strains, which is a scalar version of the strain tensor in a particular alloy. These are measurements. And to clearly identify very large peaks of this strain field. The right picture, it's derived from here, in which we just kept the effective strain constant and equal to its maximum within each grain, and also show the geometry of the grain structure in the polycrystal. So let's talk about stochastic problems. As I mentioned, I look at two aspects: analytical and numerical models and methods, and then a tool useful for analysis finite dimensional models. example of input-output relationship in stochastic problems. This is for a dynamic problem in which the output, it's a real value process, and the quantity of interest can be the maximum of this process over a bounded time interval. Generally, the distribution of Q, this quantity of interest, is unknown. Analytical methods for calculating that distribution are available only in very special cases. For example, if O would be a Brownian motion, then you have a closed form solution. Numerical methods cannot be applied directly because both input and output have infinite stochastic dimension. They are uncountable families of random variables indexed by time in this case. So what we can do is to construct a numerical version of the post problem in which we represent the input by a finite dimensional model called here IN, which is a deterministic function of time, which depends on n random variable z1, zn. Once we have this model, we can calculate the output, which is going to be also a finite dimensional model, and the corresponding quantity of interest. If somehow we can show that the numerical version of the target converges to it and goes to infinity, then Qn can be used as an approximation for Q, provided that n is sufficiently large. There are many finite dimensional models. Here there are some examples: linear interpolation, truncated KL expansion, truncated spectral density for an arbitrary target process which has finite variance. What I like to emphasize is the following things. First, we rarely know the true law of the target solution, O of T output, and the quantity of interest. We only can obtain numerical versions of it via calculations. To approximate the target by numerical version, we need some sort of convergence. And the type of convergence we need depends on the objective of the analysis. If we are interested only in the first 2 moments, we only need this sort of mean square convergence. On the other hand, if we're looking at the extremes of the output, that is this random variable Q, we need much more. And what we need is that the samples of the numerical version of the output and the output itself to be similar to each other. That is, under this metric, when n goes to infinity, the probability to go to 0 with unit value. So the focus in this talk is on the extreme. So we are going to look at this type of distance between numerical samples and target samples. Method for estimating extremes. This is a selective set of such measures, methods which are relevant to our discussions. I divided somewhat arbitrarily into statistical and stochastic methods. In all cases, the objective is to find or estimate the probability of a rare extreme event F. Therefore, this probability is small. Statistical methods. We use data and samples to construct estimates. The method we all use as frequently as possible is Monte Carlo. It's simple, general, non-intrusive, guaranteed to converge. But this has limitations, particularly when dealing with the extreme, for 2 reasons. First, output samples in realistic problems involve solution of complex stochastic equation that is time-consuming. Extremes are rare events. Therefore, they require large sets of samples for estimation. An example, if X is Bernoulli, a variable, 1, 0 with this probability, which is much smaller than 1, and we try to estimate the probability from sample of Xi, the corresponding estimator has this form, in which Xi are an independent copy of X. The estimator is unbiased, which is good, and this is the coefficient of variation. If we put some numbers in, we can easily see that we need about 10 to the 6 sample of X to estimate probability of order 10 to the minus 4 for a coefficient of variation of the estimator under 10%. So this rule out Monte Carlo if our Brownian motion, our Bernoulli variable is this form where O is the solution of a complex stochastic problem. Extreme value theory. The quantity of interest for the extreme value theory is the maximum of a set of independent, identically distributed random variable. A similar quantity of interest is in the central limit theorem, just the functional form is different. We're looking at average rather than extremes. Both theorems deliver asymptotic results, that is asymptotic distribution of Mn and Xn when n goes to infinity. For our interest, we are looking of the asymptotic distribution of Mn, which under proper scaling and shifting, it's a generalized extreme value distribution, which has this form. There are three parameters here: location, scale, and shape parameter. To implement this method, it requires very simple calculation. We use data to estimate the defining parameter of the distribution, and then use this parameter in the form of a GEV and obtain an estimate. Variation of this estimate is a peak of a threshold in which we retain part of the data, that is data larger than a certain threshold. There are some difficulties with this approach. First, to have good estimates, we need relatively large sample sizes. The most difficult part is to estimate the shape parameter, and the shape parameter controls the tail of the distribution. And the validity of this asymptotic distribution is questionable when we deal with problems, realistic problem in which n is not infinity, but is finite. Here's an example. Suppose that xi is either Gaussian or gamma, and n is equal to 100. Of course, we can, if we know the distribution, we can calculate it exactly. But this is not done in application because we have to estimate f, and small errors in the tail of f result in very large errors in ML. Here's how the GEV estimate works. The solid and dashed line are the exact values for Gaussian gamma. And we use 50 sets of sample of xi, Gaussian gamma of size 100, estimate the GEV parameters, use the distribution, and the stars, red star are the distribution. This when we generate it from Gauss and from gamma, and they converge to the correct distribution. We know that converge. The problem is the rate of convergence is unknown. That is how large n has to be in order for the error to have a certain value. There are extensions available, dependent sequences, and multivariate extreme distribution, and we are going to use the later on. Stochastic methods, they require some reformulation of the original problem, and we talk here of two types of methods. Subset simulation. Idea is quite similar. We construct a sequence of decreasing event to the event of interest, that ray event, and based on properties, conditional probabilities, we can rewrite the expression f in this form. The first probability can be estimated easily by direct Monte Carlo because f1 is not a ray event. And so this probability, this is where the computation problem is, because the estimation of conditional probability by direct Monte Carlo is rather tricky, and various algorithms have been proposed to solve this problem, and they have different efficiency. We are going to look primarily at importance sampling, which has a similar idea. That is, we try to construct a new measure under which f is not a ray event anymore. So if it's not ray, that is, we can estimate it from a relatively small set of samples. I'll talk first the finite dimensional problem and then infinite dimensional problem. For finite dimensional problems, the theory is provided by Radon-Nikodym derivative. The quantity of interest, this is a ray event V, which is a real value random variable depending on a vector Z on this probability space, is larger than F. So V is large enough to be in the tail. So the quantity of interest under the nominal measure, that is this P on which Z is defined, has this form, and we stay with the assumption that V it's the F it's a ray event, that is this probability is much smaller than 1. And we try to construct a new measure Q on the same measure space such that F is not a ray anymore. F and Q denote the density associated with these measures. They have to satisfy conditions, otherwise the derivative is not defined. And the simple chain of equalities, which we have seen it before, shows that we can estimate the probability of interest on the different measure, that is measure Q, if we modify the integrand. The estimates, resulting estimates based on the original and the intensity, the modified measure are shown here. The samples are from under P or under Q and the corresponding estimates. For one dimensional problem, it's very easy to do this construction. Example, Z is normal, V is this mapping, and that's a quantity of interest. The density of VZ is shown here, solid line. And of course, if we go to V much larger, that is in this region, that becomes a very rare event. Therefore, one needs very large number of samples to obtain estimation, good estimates. And here, exact value, in this case, of course, we can calculate it exactly. If we try to estimate this probability under the nominal measure P from 10,000, these are the numbers. Eventually, when we go far in the tail, we are not going to see any failure event, and therefore 0. And if we change the measure, on the other hand, the estimates are continue to be adequate. We will simply do the following. We center Q on the threshold V. So anytime when we move to the right, we still generate sample, most of the sample in this area. So we are going to be to have values of V smaller and larger than the particular value of V. It's getting difficult when you go to higher dimensions, and it doesn't mean necessarily that if you do important sampling, is going to be better than straight Monte Carlo. Here there are several results or available data, available algorithms, form zone years back. Currently, various optimization algorithms are used with the objective to identify parameters of postulated family of parametric distribution. For the infinite dimensional problem, as you can imagine, difficulties arise. Of course, it is a very remarkable result, Girsanov theorem, which conceptually is simple. All it does is take a diffusion process and changes essentially the drift such that more and more samples are going to exceed the threshold. So conceptually simple, implementation is rather difficult and involves specialized techniques. That is, we work in with Ito calculus, integral differential equations. We suggested an alternative approach, which is based on finite dimensional models. And this is an input-output relationship we've seen before. INON is finite dimensional model. The other are the target. Infinite dimensional, these are finite dimensional. So if we will be able to show that the outputs, numerical versions of the target version are close to each other in a sense shown here, then we can use numerical method to estimate extremes. Moreover, since finite dimensional models, on finite dimensional models, we deal with finite number of random variables. Everything we do with finite problems, finite dimensional problem, we can apply for this infinite dimensional problem. So I'm going to spend a few slides on data-based importance sampling. quantity of interest as before, the probability of a ray event, similar definition, that's the ray event. V, where it's a V of Z, it's a real value random variable depending on this random vector defined on the probability space. P is referred to as a nominal measure. And that's event whose probability content we try to estimate. That is all the Z's, we are in the space Z in which this condition is satisfied. And this set, shown here with solid line, is called the set of interest. So we want to estimate the probability content of this set of interest. The plot, the picture, it's in the Z space. We are going to consider also a surrogate, which is a very crude representation, V tilde of V. But you can generate sample of this V tilde very cheaply. It's very inexpensive. And the analog of this set, it's has the same name, but with a tilde on the top. And it's required, is based on the surrogate samples. In the picture, we see also these two for two different thresholds. Here's a property which just assume this true for a moment, and then we see how it can be used. If we can find an M such as the distance between the actual sample of V and its approximate are smaller than M, almost surely, then this picture holds. That is, if you add M to the threshold V or subtract, you have this sequence between these three sets. This is included into the set of interest, and the set of interest is included in this. Therefore, the probabilities have these properties. So this is what we are going to use to construct the algorithm for estimating the probability of event F. Let's suppose for a moment that we invent measure an important sampling measure Q, which, for example, is placing an equal number of samples on average inside this set and outside it. That is something similar to what we did in one dimension. Of the samples which are inside, some are going to fall in this subset. In this subset, provided the property is true, we can use surrogate samples, because if Z is here, we know that the condition it's also in Z tilde, therefore it's in F. On the other hand, for any Z in this donut shape between the dotted lines, we are not sure because the surrogate has error, therefore we have to use the exact representation of V, or accurate sample of V. So this is what the algorithm is going to do. And what I just said here is going to be repeated in the next slide. With one simple change, instead of using Z, we are going to use Z0, which is represented by a very, very, very large set of sample of NT, because we are doing finite M exists, but is not known. So I'm going to construct Q exactly as I said, to put equal number of sample inside and outside this set. And the algorithm is going to do exactly as before. This is an estimator, important sampling estimator, based on NIS samples of Z0 under Q. And we split it in samples for which we can use surrogates, that is sample falling in here. Samples not falling in here, we have to use actually the correct samples. If M is not unknown, the same idea can be followed. But of course, we have to do some iterations. Typically, the actual distribution of VZ has heavier tail than that of the surrogate. And if we start with M equal, we start with M equal to 0, both these sets coincide and to be inside V, and they are going to increase. As they increase, the more and more samples are going to fall into the set of interest, and the probability will increase. So this iteration process, instead of explaining in abstract, I'm going to get back to it when we are going to talk of a particular example. Extreme of random processes. As I mentioned, I'm going to first look at what can go wrong when we deal with numerical methods. And once we've done that, we are going to look at what exactly requirements numerical model must satisfy to be used for extremes. What can go wrong? Well, first, partial characterization is insufficient. Example, we have the same dynamic system driven by Brownian motion in compound Poisson process. Compound Poisson process consists of sums, random sums of IID random variables, where n, it's a homogeneous Poisson process with intensity lambda. And they have nice properties. It can be shown that as a compound Poisson process under proper scaling converging to Brownian motion. But what we want to look here is following two items. First, under some conditions, if we take, for example, these jumps to have zero mean and to satisfy this condition, the Brownian motion and the compound Poisson process have exactly the same mean and correlation function. Since the system is linear, the states of these two systems have exactly the same first two moments. Linear random vibration theory. So what I'm going to show it in the next slides, sample of C and corresponding state, B corresponding state, and the histogram of the extreme of these processes for different value of lambda in terms of C. The very first, there are going to be three columns. For very first lambda column will be for compound Poisson process, lambda 05, lambda 1, and so on. So this is compound Poisson process, higher value of lambda, Brownian motion. Sample is of the input, sample of the state, a histogram of the maximum of the state. It's no reason to comment on the differences between samples. And the histograms are also very different. And please note that there are different scale of these histograms. So again, everything you see in these slides are equal in second moment sense, the same mean and correlation function. But the extremes are totally different, the sample properties are totally different. Correlation is no substitute for dependence. Example, x1 is Gaussian, x2 is shown, has this expression. They are uncorrelated, but if I tell you x1, you know x2 exactly. Let's suppose that x is a zero mean process with finite variance. Of course, it admits the Kähler representation. Its truncated version is shown there. Lambda and phi are eigenvalue, eigenfunction. And zk are just random variables with zero mean and this correlation function. If x is Gaussian, so are zk, they become independent. But if x is not Gaussian, zk are uncorrelated and dependent, uncorrelated but dependent, non-Gaussian random variables. There are attempts in the literature to put for zk the correct marginal distribution, assuming dependence. It doesn't work. It's going to be approximately Gaussian. Let's take a very simple example. G, it's a sum of A and B scaled by cosine and sine, A, B, independent Gaussian, and this is a Gaussian process, stationary. They construct the following non-Gaussian process. The random variable Z, so it's a special case of what you've seen before, are uncorrelated. If you're patient, you can check it out. But of course, they are dependent because they depend all on the same two random variables, A and B. These plots show scatter plots, scatter plots of Z1 and Z3. This is the actual scatter plots. They, under assumption that Z1 and Z3 have the correct marginal, but they are independent. The probability of this extreme, solid line is a correct one. Dotted line is based on this assumption that the Z's have the marginal distribution correct, but are independent. As you can see, the tail is getting thinner and thinner because it's getting closer to Gaussianity. Extremes of processes. For this slide and following two are going to be rather technical, but I'm going to try to stay away as much as I can from technicalities, just to give you the main idea of what's going on. I'm going to refer to similarity between different processes, and they can be defined in different way. Second moment, mean correlation function. For example, we say that the two inputs, target and its finite dimensional model, are similar if the correlation function of the FD model converges to that of the target. Finite dimensional distribution, similar convergence, finite dimensional to the target. And samples, this is a much stronger property. We want the difference or the discrepancy between samples of the FD model and the target samples measured with a submetric to go to zero and then goes to infinity, almost surely. That is for almost all omega. Depending on the objective of the analysis, we may need different type of similarities. For example, if we are interested only in second moment analysis, it suffices to have the mean and correlation function correctly for solution of linear random vibration. That is, 1 is all we need. Mean crossing rate, 2 is almost all we need. We need that plus some condition requirement for the smoothness of the samples and of the process. We need the process to be mean square differentiable. For extreme, we need a lot. That is, we need 3. Because we need to be able to show that for sufficiently large n, samples of FD models are similar to that of the target. Same thing for the output. So let's talk first about input and then look at output. For the input, to have this, to be able to replace or substitute a sample of I, the target, by sample of FD model, we have to require quite a bit. And the whole theory, essential parts of the theory are in this old fantastic book by Billingsley. And they require mean correlation, finite dimension distribution of I to converge to that I of the target process. So this is just the beginning. We want much more. We need weak convergence of FD model to the target in the space of continuous function. This is very similar to the distribution on the real line for real random variables. It just, instead of looking at real numbers, of numbers on the real line, we look at points in the space of continuous function, and we look at the distance between the points in the space of continuous function, and this distance is measured this way. So what we want to have for a given epsilon, we want this bit set that is in which the distance, this distance between the samples of FD model and target are larger than epsilon, has a small measure. Ideally, we want much more, that what we find an n for which this measure is small, and we increase n, this measure is getting smaller and smaller and smaller with n. I'm going to give you just a very simple example. If in is this, and I is this, that is goes all the way to infinity, H and B are just uncorrelated. To have this type of convergence, which is called weak convergence, we require two things, that these two series to be convergent. And this is where new Ks are defined, and Ck are the variances of these A's and B. I want to emphasize that this is stronger than finite variance, and this is stronger than mean square differentiability. So we need more than that to have this type of convergence. Going right now to the solution, the outputs. Let's look the output being this diffusion process, and the input, the Brownian motion. Its finite dimensional version is shown here. has this expression with a modified drift. And please note that even the structure of this equation is different. This is Ito, this is Stratonovich. And Bn, the finite dimensional model, has this expression can be constructed from the eigenvalues and eigenfunction as a correlation function of the Brownian motion. The main results are the following. I'm just going to state and I'm not going to show any proof. First, we know by Mercer's theorem that this true, that is, we have this convergence and mean and correlation function, and they imply the convergence of finite dimensional distribution. But we also have shown that the Brownian motion, this finite dimensional model converges weakly and almost surely. That means we can approximate samples of B by sample of this finite dimensional model for sufficiently large n. Having that said, the same thing can be shown by using Wang-Zakai theorem, original version of this, to show that even sample of xn can be used as substitutes for sample of x. And under this condition, we can estimate extremes of FD models from finite dimensional models of these processes. And then we're ready to look at some applications. As I said, I'm going to present two such applications. The first, it's on the Versum model, and the second on fragility. Quantity of interest, as before, it's this extreme of the process. The state is defined here. The finite dimensional model associated with a pose problem is illustrated here. Ito equation, Stratonovich equation, and this is a finite dimensional model of the Brownian motion. We just talked about it. And we prove that we have the required convergence, that is almost sure convergence, the space of continuous function for both the input and the state. That is, we have satisfied this condition. Therefore, this is true. That is, we can do this approximation. So now let's see how we are going to use all this stuff to construct important sample estimates of these probabilities. So to minimize calculation, what we want to do to use small sets of high fidelity samples, that is, sample of this process obtained by, for example, Euler schemes with a very small time step, and large set of low fidelity or surrogate samples. With this low fidelity or surrogates are surrogates of the finite dimensional models. We want to get much cheaper than that, but in order to produce a large set of such samples. Any surrogate can be used. We use SROM surrogates. And I also must say that the measure Q is based strictly on low fidelity models. Therefore, it can be very easily constructed. Numerical example are for these values. Left and right panel shows sample of the target Brownian motion and the corresponding finite dimensional model of this process for two values of the truncation level. And below it's an error, which is a metric in the space of continuous function. As you expected, when n increases, the error decreases. These two plots are for the state, as before, the same meaning obtained by our scheme and the solution of the finite dimensional model. Some scatter plots. Of course, these plots I just show here for illustration. In real application, we never see this sort of plots. If we have them, we use all the data, the actual data, but usually don't see them. I just want to illustrate how these things look like. So this is a relation between the exact sample of V and the finite dimensional model. And this is finite dimensional model and its surrogate. Of course, when you go further away down this line to surrogate, the differences between target and surrogate increase, and they tend to miss extremes. Some numerical examples are for the numerical example is for value v equal to 9, and the probability we first state mentions this target probability. For this value of the threshold, it's the order 10 to 10 to the minus 10 to the minus 5. We use 10 to the 7th samples of X to estimate this probability. If we use just low fidelity samples, that is surrogate samples, we are going to get 0 based on the same number of samples. IA estimates based on 1000 samples are illustrated here. So what's shown here, this M, you may remember that M, if we increase or decrease the size of the donut when we modify M, this is a target, that is this number here. Solid line is the average of the importance sampling estimate, and the dotted line, it's the coefficient of variation. So what we've seen in here is as M increases, on average, the importance sampling estimate reaches a level and oscillate above the exact expression, and the coefficient of variation increases slowly with M, and then becomes increases very sharply with M, and increases very sample very fast with M, and this is a reason for this increase. So let's go back to the original picture, which it looked. As M is very small, this C tilde will be either included completely in the set of interest, or it's going to have an intersection. As M increases, eventually when you reach M star, it's going to include the set of interest, and therefore beyond that point, the probability content of the set of interest cannot increase. But something is going to happen. We keep the number of samples of Q constant. So as this set increases, fewer and fewer samples are going to fall into the set of interest. Therefore, its coefficient uncertainty in the resultant estimate is going to increase. So this is the trend. M increases, eventually the estimate is going to increase till the set of interest is included in this set. And if we continue increasing, fewer and fewer samples are going to fall in the set of interest. Therefore, the coefficient of variation is going to increase. So this is what you see here. Target, on average, the estimate, importance sampling estimate increases and oscillate very closely about the target. Coefficient of variation increases. At the beginning is very small because the set in which we put sample is very narrow. Therefore, there is not much variability. Then it explodes because the number of sample decreases. Seismic fragilities. A few notation. Seismic ground acceleration, X, it's a vector value process for an arbitrary structure subject to this ground acceleration. X DOF is a displacement of simple linear single degree of freedom system subject to A. And this is a typical intensity measure used in fragility analysis. That is a maximum of this response. Fragility is a conditional probability. That is, the probability that a damaged state enter a particular state given the intensity measure. And these are the two random variables. They are dependent, of course, as function of A, but they are likely to be weakly dependent because these two processes are very different from each other. Just a picture to illustrate this idea. This is a single degree of freedom system, and the idea of fragility is to estimate from the response of this simple linear single degree of freedom system, the response of a very complex nonlinear structure to the same ground acceleration. Intuition suggests that this doesn't work, and let's look at some data. I'm going to show two sets of scatter plots between D and SA for two dynamic system, the Duffing oscillator, the demand parameter, and the intensity measure. For increasing value of A, that is, you just scale it up. When A is very small, there are very good agreement between the two because the nonlinearity doesn't show up. As you increase, the nonlinearity participate and the relation between the intensity measure and demand parameter deteriorate. Similar situation for another system, Bucon model, for two types of earthquake. This what happen when we increase the intensity of the ground motion. Again, demand or intensity measure versus the demand parameter. We are going to use right now some idea of multivariate extreme value distributor to quantify the dependence between these two quantities and to determine whether intensity measure is meaningful. Idea heuristic summary of this theory, say x1 and x2 are positive, identically distributed. You can represent them in polar coordinates. Same thing for the data. And you can construct histograms of the orientation for large data, this data with position vector much larger than a particular values. The histogram of this thing is going to indicate whether there is or there is no dependence between large value of x1 and x2. So for example, if this histogram is concentrated at 0 and pi, half pi, then is no way for x1 and x2 to be simultaneous large. Either one is large and the other one is small and vice versa. We are going to apply this idea to the intensity measure or to fragility, in which x1 is going to stay for intensity measure and x2 is going to be one of the demand parameter, and determine how this function. But first, a simple illustration, further illustration of the histograms. These are the two random variables, x1 and x2. From if lambda is large, if you take lambda equal to 1, this will be perfectly dependent. Lambda is small, large lambda, small lambda. So large lambda, the dependence is very strong. This is a histogram, the spectral measure, highly concentrated, somewhere the value of theta. As you go further and further and lambda becomes smaller, in fact, the limit on lambda is equal to 0, they are independent. And these are showing the data, just data larger than the particular value of V0. The spectral measure becomes concentrated around pi, half pi, 90 degrees, and 0, indicating lack of correlation. I'm going to show the same plots for the intensity measure and demand parameter for the Bucon model, which you've seen before. That's the input spectra. These are the data, that is scatter plots for intensity measure and demand parameter, same intensity. And this is what we found. Repeat of the scatter plot we've seen before, and the circles simply represent just the data which have been used to construct the spectral measure. This spectral measure have resulted concentrated about 0 and 90 degrees, which clearly indicate that the dependence between large value of intensity measure and demand is very weak. Therefore, particularly for large earthquake, when it's very important to predict accurately the performance of buildings, the fragility, current fragility, provide virtually no information for this type of events. All kinds of things have tried, for example, to select a particular sample of the ground motion to improve these things. It seems that it doesn't work. In fact, the random selection of ground motion does as well. Fragility also can be constructed over several values of SA. Now, this also has been shown to be unsatisfactory. The only thing which works to construct fragility surfaces on the parameter, defining parameters of the seismic ground motion process. And I'm going to stop here and thank you very much for your attention. And I hope you are going to ask me questions.